2-3 minutes, but let me just begin by saying that I've received a number of emails from some of you regarding conflicts of the designs or spatial accommodations. Unfortunately, I have to apologize. I don't have to handle this for me, and I have many other things in my email boxes. I often overlook emails that come from students of this class, 30 or 40 students. So I've asked my TAs to keep track on all those requests. I'm here to tell you if you can pass the word to all of your first class. If you have any requests to this class, conflicts of design, restaurant, when you send an email to me, please copy to TA as well, TA@gmail.com. So this way, TA can keep track on this, so that we don't overload you. So if I don't reply to you, it's not that ignoring you. That's simply unable to reply to every instance. And too many mailbox. Sometimes email got into spam folders and unexpected. So I know I missed something. So please send it to TA. And by next week, I think the TA is going to tell you with a poster on Blackboard. By this Friday, so we would like to receive all the requests for the example in person last Friday that we have conflicts, so we try to resolve. The general policy is, as I said earlier, if for reason that beyond your control, reports, that you cannot make the exam at 7 to 9 p.m. in the evening on March 4th, that's one thing. And we'll try to accommodate this with another time within the day. And if we cannot schedule you, or you cannot schedule to that day, then have the makeup design after that day, which will be in the form of oral design. And this is a very logical answer. So anyway, situation the question. So we're going to continue to have 2 more lectures today and Wednesday. So what I will do is that I will take these 2 lectures and give you some examples of the alternate system. And this system that I do research on. And today we're going to talk about the first part, and then Wednesday we'll kind of talk about the second part. Now, why do we study the alternate system? That's not simply because I do this for you. This is a system that all of you should be very interested in. Right? This is a system responsible for speech and language. The very fact that we communicate among ourselves depends on the alternate system. It also is very important for music, singing, and poetry. This is a subject that just began to emerge in scientific research and in this literature. And perhaps some later time, I will share with you some of you. And I know many of you have learned the instrument. If I were to take a quiz, about 70–80% of you were done this. But we actually knew very little of how the birth process is. This is a major area of research in audition that just began to be taken seriously in recent years. The third class of problem that we're interested in is the deafness, tinnitus, stuttering, schizophrenia, and autism. All of them have something to do with disease and dysfunction and deficits of autism. So those are the reasons we study this system. Now, this is one of the 3–4 major sensory systems in the body. Another one is a visual system, you hear. And so the sensory system for touch, and the respiratory system, so so we'll talk about all of them in this class. Now, how do you analyze our system? So what we do today is to take you through a sound that you are familiar with as engineers, and walk you through the ear and what's behind the ear, explaining how does the brain convert this mechanical vibration into something that your brain can understand, which is the spectrum or action potential we spent time discussed last Friday. So how do you quantify sound? So if I take a piece of music, any music you name, just for example here, and plot this in this 3-dimensional plot with time, frequency in these two axes. And the height of the piece or reload indicates the strength. So the real music is like this. Unfortunately, somehow my laptop isn't playing. I'm trying to play a piece of music for you to see what you can hear. But you can appreciate this three-dimensional part. Now, if you take something much simpler, like a tone, like this, right? Fixed frequency over time. In this part, it will be just one line. Fixed frequency over time with constant amplitude. So tone is the simplest sound one can generate by physical means. Tone, that is the simple sound we call it pure tone. And then music and speech much more complicated. Now, here is an example of speech. We're plotting this three-dimensional plot. Since now we're plotting the 2D with properties on the height of energy. Okay? So this is a sentence, what you can read. This is an English sentence. Only a millionaire can have a house with one window of the sunlight roofs. Okay? So you can see this is what we produce. Now, if I don't tell you what is the sentence is, it's actually very difficult for you to read this. In fact, just trust me that it's very difficult for a computer to actually read out what this is. If I speak this in our language, and if you speak it in our language, Spanish, Korean, you name it, French, you look at this, the more it's the same. Because as we will be talking about, all of this are produced by a little track here, which we share amongst mathematics. But another thing interesting here, which I just gave you a little hints now, I'll come back to this. What makes speech interesting is the following. So there's something we call the pitch. That is when we talk in a natural language, we actually modulate. So we say only a millionaire, only a millionaire. You can modulate many ways. Well, meaning doesn't change, but we modulate our voice here that we call pitch. Will turn to be something very important and interesting. We'll come back to that now. So a normal speech like this one will contain what we call spectral temporal information to encode the meaning and the pitch to encode the emotion or energy. Now these days, speech synthesizers, your iPhones and Android phones are very good now. When I was graduate student many years ago, and speech synthesizer is not as good as now. So, but in hospital, all the elevators have a speech synthesizer. I mean, if you go up to the hospital, we still have that. You push a button, they say, floor 3. Right? Now it's very natural. But early days, it's very monotonic. It's made by Texas Instruments. My professor in digital signal processing always teases that. So if you listen to that, that's Texas Instruments voice. It's very flat, level 3. Right? So no pitch. Okay. What is missing is pitch. Okay, which will become natural. And then we'll come back to talk about how the brain processes it. So a natural speech is spoken by a real human being sounds much more smooth. Now, these days, you can produce that kind of speech with a phone now, naturally, very, very well. These days, so that's quite different. That's what people will code this. Now, the reason pitch is interesting is because it's linguistically. The example I gave you last slide is English. If you take a tonal language like Chinese, which is the native language I learned when I grew up, the pitch becomes very crucial. So this is my favorite example to demonstrate to you how sensitive your ears are. Okay. So my last name, W-A-N-G. If you speak this in Mandarin, it'll be one of these four. So I'll mimic for you. Is Wang, 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 Wang. You got it? Okay. Let me repeat. Wang, 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 Wang. What's the difference? I'm shaking. Second time, I simply repeat the first tone 4 times. So don't feel bad if you don't hear it. Many years ago, when I come here to be interviewed for professorship, I gave lectures in the building 2-3 blocks from my undergraduate building. It was a group of distinguished neuroscientists, professors sitting there. I was talking about how the auditory system processes cue. So I taught this example. You can tell them my name is Wang, 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 Wang. And I look at everyone is puzzled. Then I figured out no one actually understood what I was talking. Okay. So if you're a native Chinese speaker, then when I say Wang, 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 you hear them, each of them distinctly as musical notes. This is very much like the musical notes you learn. So what did I do? What I did is change the voice contour of the pitch. So if you follow my little point to module pitch, then you find that it's actually pretty straightforward. There will be constant pitch. Wang, 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 Wang. Okay, that's it. Okay. This is learned. It's not genetic code. And after you spend months in our life, you learn this. Okay. But what's interesting following, in common language, not only Chinese, but other languages as well, pitch becomes what we call linguistic cue. You use the code information. Because in my lesson, if you speak correctly, it means king. Okay. I'm not making up, you can't. But it could mean vast, could mean name, could mean forgot. Right? Just one piece difference. Now in English, pitch is called paralinguistic cue. It is linguistic, but it's not a fundamental. What is it used for? For example, when I say something, when I ask a question, did you finish your homework? You say, yeah, I did. I say, are you sure? I simply raise, I'm skeptical. You say, I'm sure, with a foreign piece means confident. It turns out when people design lie detector, if you were ever design lie detector, put a microphone, say, talk. This will be one of the top parameters you detect. Because when it becomes panic, when you miss your flight at the airport, you pick up phone call your parents, call your friend, say, I missed my flight, so what's wrong? It's your pitch, it started chunking. Okay. So pitch actually carries not only linguistic cue, but emotion and other things. So this is something that we'll come to revisit. And I say this is a learn part. Now, how does the audio system process all of this? So I play a sentence here. Today is a Friday. No, today is a Monday, right? This sentence has a lot of information from the spectral temporal patterns that tell you what does it mean, to the pitch tell you it's a male speaking, and to the contour pitch tell you that the speaker is quite calm, not panic. All of this I extracted by audio system. Now, imagine this whole system is a computer. If I say, go ahead and run a computer program, extract all that information. It's very difficult, very challenging, still today. But it's how that audio system does. So here's an anime of audio system, and we're going to walk through together. So start from here. This is somewhere your ears. We'll show a better picture next slides. Within which the device apparatus we call it talker. Okay. Here's air. Sound coming through here. Within the talker, the mechanical vibration of sound is converted into action potential. Okay. This is the major goal of today's lecture. We discuss how this happens. Then after that, then the signal will go travel through this stage called the auditory nerve. Okay. Now beginning from here, all the signals are in the form of action potential spectrum. This is why I discussed last Friday. Action potential is so fundamental. Because after the first stage, every bit of information is carried on by action potential. So from here on, you will go to the next stage called the cotton nuclei. And MS or aerosol, don't bother by names here. And computer corrects the thalamus all the way to the place we call auditory cortex. This is a very long pathway. So now if you take an analogy as a computer, this will be the microphone of the computer. All of these are the processors, one of another, all the way to the brain. So by the time you understand my voice, what I'm talking about, you are relying on the processor here, all the 7 stages away from the beginning. So the system. Now later on, in about 2 weeks, you will hear from Dr. Ed Connor about the visual system, and bear this in mind. In visual system, what equivalent to talker is retina, the eye. And what is equivalent to auditory cortex is the visual cortex. And you will see in the visual system, from here to here, it's just one straight line to the thalamus. Okay. So the first important characteristics of our auditory system is that it has a longer subclinical pathways. Okay. So later on, after you hear about the several systems, I'll take maybe one lecture or so to compare them, because it's an easier way for you to appreciate how the brain is designed. It's just compare different systems. What's the difference? So whenever possible, I'll highlight the difference and similarities between the different systems. So this is one unique about operating system. Longer subcortical pathway. Subcortical means anywhere below the cortex. This is called cortical subcortical. Okay. So we'll talk about this in on Wednesday. Now, for this class, and you're gonna start running into from here, and many in my lectures, many terminologies. If you're class, all of them, not anatomical terminologies. I do not expect you to memorize it, so don't bother with it. So I swear to myself when I was a student, one day when I become a professor, I would not ask a student to memorize this, because I simply hate memorization. So, but whenever I show something that's important, I will explain. If you understand it, you will know it. Okay? But I'm not going to simply test you to memorize it. The fifth stage in our pathway is what? Okay? This is what you can do eventually when you go medical school. Some of you will. In medical school, the exam will be they show this, and with no letters there, and then say, show up this stage. What is that? Then you have to write down. That's pure memorization. You have to do it, but not in this class. Now, the second unique feature of our system is that the signal into the ear are spectral overlapping, time varying. So let me explain to this. So when I show you a visual signal like this one, I say, look, what is this? This is a laser pointer. So this, okay. And if I put my hand in front of this, that's what it is. You say, well, you won't see my hand. You don't see this. Okay. Most of visual signals are not overlapping each other unless you put transparent sheets of paper here. Okay. In auditory signals, everything is all spectral overlapping. So that means if I put a microphone here, ask somebody to speak your signal recorded here, then ask somebody else to speak, signal coming here. If you look at the signal here, the two voices is on top of each other. Because of vibration in the air, it's all transparent. This is a problem engineer called spectral overlapping. That is, if I turn on my microphone, my laptop, I tell everyone, just begin to talk. My microphone will pick up all of your voice on top of each other. The 80 linear, right? As an engineer, you know, if you do further analysis, the structure is overlapping, not because all our voice share the same bandwidth. This turned out to be a killer for speech processing by computer, by cell phone. This computer has no idea whose voice now because it's all energy. That's a major signal processing issue of an auditory system, unlike any other system. The second point here is time variable. Okay. Again, if I take a visual signal as an example, I give you this, I don't move it. I say, what is it? Or you can describe the object. Of course, I can generate a motion. I don't have to. I can define a visual object without a time. But in auditory signals, can you define a sound without time? It's impossible. The simplest sound, like pure tone, is moving as a function of time all the time. So sound, acoustic signal, is like the water in a stream. They're moving all the time. Okay. You may not have thought about this, why this is an issue until now. The issue is fun, which we'll deal with later on. Remember, in our brain, we talked about last Friday, all the signals are processed represented by action potentials. Action potential is the time variant spectrums. Okay? So here you have time variant signals. Now I'll give you another time variant signals. The sound, ooh. You have two signals over same time axis. This is the same time. How do we represent it? In vision, I say, what is this? This is front of my hand. Later on you will learn. In the retina arm, when you see this one, there's action potentials. Blah, 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 blah. I turn back, what is it? Back of my hand. Blah, 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 blah. The two signals, by checking the difference between two signals, you know it's the front or back. There's no time here. But now in sound, I say, ooh, there's a time sequence. Good. I say, ooh, there's another time sequence. You have two time sequences, there's a two time sequence. This actually is actually computationally a very difficult problem. And we'll tell you how the auditory system solves this one. Okay? In fact, the first exam, first homework you did that I gave to you has something to do with this. And you will see later on when we touch upon that on the literature. The third point that makes auditory system unique is that sound enters the ear from anywhere, anytime. Now, you may not be fully aware of this until now, that your ear actually can never be turned off. Okay? So whether you fall asleep or pay attention to something else, your ear is always on and all day on from by up and down. Okay? I often joke to students when I give lectures, larger lectures, a student falling to sleep. I don't know why, because whether you're falling asleep or not, my voice will penetrate the audio system. Right? Because you have no switch. Invasion will have to eyelid. If I don't want to look at someone, I close my eye or turn my head around. You can't. Also, your ear is open 360 degrees. It turns out, our research shows, if you look at neuron in our brain, the neuron is tuned to front, side, back, up and down. Okay? We have neuron, full of neuron turned to like radar. We have our system like internal radar, turn everywhere. One of the very basic examples to show this function is what is called cocktail party. Okay? You might have this experience. You go to a party, chat with your friend, fun with. Suddenly, somebody behind you begin to speak. It could be your girlfriend, boyfriend, or someone else of interest. Suddenly, while you're still pretending to speak to people in front of you, your entire attention is there. To the point, actually, what people talk to you right in front of you, you may never hear. You don't hear. Because internally, you just turn your attention away. That's called cocktail party. In other places, sensory system, in vision, if I do so, you have to turn around. Right? In audition, no. This is something only auditory system has in our brain. Why do we have this? To say simply, that in ancient days, in our ancestors, they don't live in room like this. They don't have a lock on their apartment. They live on the wild tree, under the trees. If when they fall asleep, they cannot see anything. Of course, eye closed. If they cannot hear anything, they'll be eaten by tigers. Not good, right? So auditory system, probably for that reason, involved to stay alert all the time. Now, as an engineer, if you design a computer like this, it'll be a disaster. Just like your computer, no matter what you do, microphone is always on 24/7. You think about this, right? It's actually a problem. Nobody wants it. In our computer or cell phone, we don't want to turn off. But you are never bothered when you're falling asleep. Think about this. So there's actually a lot of science behind this. We do not fully yet understand how the auditory system operates when we don't want to listen to something, we want to fall asleep. It's all operating internally without a physical switch. The last but not least, the auditory system is not a pure sensory system. It's a hearing, speaking, sensory motor processing. We'll talk about this. That whenever you talk, when I talk about, you hear yourself. It turns out, hearing yourself is crucial for you to learn foreign language, to sing properly, and to modulate yourself as you wish. Okay? So we do not operate just by listening. We speak listening and couple together. And then we'll talk about this on Wednesday. So those are the 4 points that compare with auditory system and other systems. Now, these are the points that if you take the neuroscience textbook we assign to you, they actually don't talk about these things. We talk about this because this is sort of a research perspective when you put a system in comparison. You keep these 4 points in mind when you learn visual and vestibular and our system. See what is similarity, what's the difference. That's something and we would like you to understand throughout your homework and exam exercises. Now, I said earlier, the simplest way to produce the sound is by generating sinusoid. You don't need MyType to do so. When you're younger, you might remember if your ear has some issue, the parents will take you to a physician. They take the tuning fork, and hit one, and it produces sound. And this is also something you probably likely have seen this in high school physics class. Just to produce a sinusoid. That's a simple sound, and of course, you all know how to analyze this by its frequency, amplitude. And there are different sounds from sinusoidal to square wave, to pulse trends, to white noise, all of that. And all of this knowledge is extremely useful. So if you're an engineer, you are naturally suitable to study auditory system because this is all the knowledge you learn from signal processing, signal system. can be applied here. Very nice. Now, here is a plot that just simply show you the scale of the sound, how loud sound will be. And generally, when we speak, we speak in a moderate sound level. And in normal conversation, it's about 70, 60 dB. And you look here, loud rock concert hall is 100 plus dB. It's too late now, but if you have gone to too many loud rock concerts, it's nothing good for you. So whenever have a chance, tell your friends, oh, when you grow up, when you have kids, tell them, don't go to the concert hall. That's too loud. When you listen to some louder than 90 dB, 100 dB, even for a short period of time, you will end up with lasting damage, sometimes hidden damage in your ear. So the comfort level, what we hear, is 60, 70, 80 dB, but not very loud. You know, when soldiers come from a battlefield, often have gunshot wound because they hear too much gunshot, their ear start ringing. So this is something you should keep in mind. Now, that's the loudest that actually many people experience when they go to concert, rock and roll concert. Now, in terms of frequency, what we hear, this is what you should be might be interested for humans. We'll hear somewhere between 30, 40, 50 hertz, all the way to 20,000 hertz. That's upper limit. And we'll explain in a few minutes what defines this. But in other species, they can, like bats, can hear much higher. And if you can look at cats, cats actually hear much higher than us. And what a cat can hear very much overlap what the rats can hear. They're prey and predators. So we as humans actually will hear, we tend to hear low range. So above our hearing range, about 22 kilohertz, we call it ultrasound. That's what we call ultrasound. Now, the way to define our hearing range is by this curve. We'll call it audiogram. This defines the hearing threshold at a given frequency. For example, at about 3 kilohertz, the sensory threshold, hearing threshold is the lowest. This is where you are most sensitive. Our speech is about this range. Now, you can hear higher frequency line, has to be louder. And the mama said this animal I laboratory study, you can say monkeys, they hear similar as us. Okay? Now, given the knowledge that we discussed in the psychological function lecture, you should be able to derive this if you ask to derive it now. You actually know enough now to derive this of threshold of yourself. And why we have so many frequency range, we use them for different purposes. For example, the pitch example I just gave to you, that's in the range about 1 to 300 hertz. Okay. It's very, very low here. The speech is about 500 hertz, 2 to 3 kilohertz. Music instrument somewhere is kind of here. So what you can see here. So there are lots of sound we can hear discriminate, but we cannot hear voice. Our voice always goes into this middle range. So the 4 questions, the 4 points I want to go through today into this lecture are these 4. How is the sound converted to neural firing from vibration? And how is the frequency sensitivity generally? When we say high frequency, low frequency, why we hear high and low frequency? Third, how is the time represented by neural firing? And last, how is sound represented by neural firing? Okay, so those are different points I want to go through. Okay. Now, to understand how does the ear generate neural signals from vibration, we need to understand this anatomy. Again, I don't expect you to memorize any term, but any term I put a red square on it once, you should pay attention, you should read and understand what it does. At least when this term is on paper, then you can explain what does it mean. So here's how it goes. So this is, if you look in front of someone, this is the ear. This is external ear, we'll call it pinna. And there's the eardrum, ear canal. Okay? So when you go to a doctor's office, look at your ear, take a look at there. That's what you look. Okay? What a doctor would see is this piece of membrane we call tympanic membrane, or sometimes we just call it eardrum. Commonly, just eardrum. Okay? And behind that is a space, and the eardrum is attached to this bony structure. If you enlarge it here, it's here. This is the eardrum or tympanic membrane. There's three bones. They function like mechanical lever. This is names here. And now what happens is that this three pieces of bones is the last one, stapes, attached to a bony structure we call it cochlear. Cochlear is the most important apparatus in our system that allows us to hear. Okay? In moments we're going to walk inside, but from this outside you can see cochlear is connected by auditory nerve into the brain. Okay? So this whole apparatus we call outer ear, middle ear, or inner ear. Inner ear is cochlear. Okay? Now let's walk through 1,000 hertz pure tone. So let's take the 1,000 hertz pure tone. You can generate by tuning fork. We see how this goes into our brain. Okay? So you have a sinusoidal vibration here, right? You know from physics, the vibration here will travel through here, eventually generate vibration in the eardrum. So eardrum will vibrate because eardrum is attached to this small piece of bone. This piece of bone vibrates. It turns out those bones serves the function of a lever, so that magnifies the vibration. So now vibration is transmitted into cochlear. The entire cochlear is bony structure, rigid. If you vibrate the one piece, as you know from physics, the whole thing will vibrate. So now whole cochlear vibrates 1,000 hertz. So then let's walk inside the cochlear. So within the cochlear, if you take cut, you can see the setting inside. So cochlear by name is because it's shaped. So if you can expand the cochlear, it's hollow, right? So if you have cross section here, it's hollow with two compartments through. But this is very hard to put in a ear. So through evolution, brain developed this is spinal is stuck in the ear. Okay? But essentially, this is this tube that just is spinal structure here. Now let's look at what's inside the cochlear. What's inside the cochlear is following. This will be one section. It's just like you expand this, color here, you look here. Okay? So you have two compartments here. That both of them are filled with fluid. This compartment is called a scalar tympani. This is called a scalar vestibular. And there's another one, third one, it's called a scalar medium. Okay. Now, what's interesting is here, on top of this compartment, there's a small softer piece of tissue on top of that. This is called basal membrane. And here, on that, the two types of cells here. Those on the left called inner hair cell. Those on the right called outer hair cell. On top of this, there's purple color tissue called tectural membrane. Okay. This is key up here. Now, following our previous slides, now we have 1,000 hertz vibration cochlear. Because the cochlear has fluid inside. When this bony structure vibrates by sinusoidal, of course, it's fluid vibrate by sinusoidal. This is where we are now. So now, next slide, we're going to watch there. So now, if you look here, this piece of the membrane, we enlarge this. This is the inner hair cell, is one row, and outer hair cell, 3 rows. Okay. So for the much of discussion in this class, we focus on inner hair cell. Inner hair cell is the ones that carry information inside the brain. Outer hair cell is the ones taking information from the brain. So let's focus on this for now. This whole piece is called a Wang recording. Okay. Just an info. So now, outer hair cell, inner hair cell are connected fibers into the brain or from the brain, and this plot show you how many fibers connect to each other. Those are details. It's not that important for now. What we like to understand is that in the hair cell, how does the hair cell convert the vibration into actual information? Okay. So now let's take a closer look at here. Remember now, the last slides we say vibration is in the fluid here. Now, since this is on top of this, then you essentially have a situation where the cochlear is a fluid. This tympanic membrane is on top, sitting on top of this, not membrane, basal membrane. Okay. So if this membrane here, this fluid here, this is hair cell. Okay. So when this vibrates, naturally this will go up and down. Okay. Except that on top of this, there's another piece of tissue on top of this. So this cannot go free up and down, but be pressed by the tissue. So when the vibration go up and down by sinusoidal, stimulation, this gets pushed left and right. Okay. This is what happens here. You see here, so the fluid goes up and down because of a vibration, pushes visceral membrane to go up and down. And this hair so present against that tectural membrane. And when this goes up, when this goes upward, it pushes this way. When it goes down, pushes this way. Now the sinusoid up and down become left, right, to left, right. Okay, so that's motion now. So the key is here. What is moved here? Now this is called hair bundle. This is hair cell body. So what you look at is the following. If you now zoom in hair cell, this is the last stage of this process. So it turns out the hair cell, hair bundle here, have channels, arm channels, that is are mechanically sensitive. So by now, for all the courses you're taking, including SBE1, you have learned arm channels, right? What is force to turn iron channel on off based on what you learned? What makes iron channel on off? Process remember? Voltage. That's standard neurophysiology. You ever know that so voltage sensitive iron channel. That is probably true in 90% or more places in the brain, except here. This ion channel is sensitive to mechanical force. Okay, this is what a very special audio system discovered only about 30-some years ago. Okay. So what happens is that this ion channel here is almost as if there's a spring. So when it's pushed this way, so when the sinusoid goes up, this pushes this way, this pull it open. So parasites flow in, the cells depolarize, everything you learned from the past apply here. There's nothing new here. Okay? When they push this way, the channel closes, it becomes hyperpolarized. So once this cell body is depolarized, neurotransmitter release here that postsynaptic regenerative action condition. From here, everything here you already know. Okay. So key here is this motion caused the ion channel here open or close mechanically. That's something to do about this. Now, how do scientists know this is indeed the case? Or you can do the experiment I followed. You can push the hair so this way or that way, and you can see current is up and down, iron current. But if you push this way, nothing happens. Okay. So this can be tested. Okay. So this is another way to quantify this. When you displace the hair, so this motion, the iron channel is open mechanically, and you have increased current, inward current. You go this way, not happening. So it's rectified. So now the sinusoidal vibration through cochlear vibration, through fluid up and down, through this motion, through this become what? Become current flowing half cycle, now flowing other half cycle. That is how this is. Now another interesting thing about our so let me finish inner rehearsal. I'll come back to tell you about this. It's funny. Let me finish this. So by this mechanism, let me stop here. So by this mechanism, the auditory system can have action potential that corresponds to only half cycle. So I leave it here now. Remember, when you have sinusoid go up and down, this will go up and down, left and right, or forward, backwards. Only this direction is open. Therefore, depolarization, therefore action potential. This direction, no. Okay. So in about a couple of minutes, we'll get to the point of what does it mean? What does it mean to what over here? So that's inner hearing cell. And inner hearing cell are the ones responsible for hearing. So when I said earlier, if you have gone to loud concert hall many times, then some of this is in your ear would be damaged. Once it's damaged, then you cannot hear. Right? People often joke there are two types of hair. It's extremely difficult to grow. One is hair on man's head. Everyone is trying. Another one is hair cell in the ear. And people are trying half century. As of today, there is no medical ways to regenerate hair cell. We're still trying. So now I see is if you lose hair cell, you lose hair. Okay. There's another way to bring hearing back by cochlear implant, which we'll discuss later. But normally, once you lose this, you lose hearing. Now, when you're getting old, unfortunately, you begin to lose some hair cells at high frequency range, and you also lose hearing. So all the hearing loss, the source is in this hair cell. That's inner hair cell. So what does the outer hair cell do? So just briefly, we don't spend too much time here. So if you think about it here, outer hair cell is here, right? So that's inner hair cell. Everything we talk about is inner hair cell. So when this goes up and down, inner hair cell getting pushed against here. Therefore goes this motion. But this piece of tissue has certain mass. Okay? And inner hair cell here hold this. So think about it. Yeah, you want to learn physics. If this inner hair cell, this thing has a piece higher here. I have 3 outer hair cells higher than this here. If outer hair cell pushes this thing up and down, it will affect mechanics here. Naturally, right? That's indeed what an outer hair cell does. This is another really special thing about outer system. First thing I told you is that this channel is mechanical, not a multi-system. Second thing is that this outer cell actually can change its length. This was only discovered in 1980s when I was a graduate by Professor here at School of Medicine Hospitals. Before that, people had no idea. Say, why do you have 1 row of inner hair cell that's only used for hair? Why do you need 3 rows of outer hair cells? It turns out outer hair cell has impulse from the brain. And if you bring the signal to here, it changes. So this experiment people did. What people did is that take a piece of outer hair cell, put on dishes, then inject a current into this. And once you inject a current into here, you can see here, the signal changes. So if you inject the current, the cell becomes longer or the shorter. So essentially, you have tectonic membrane here, inner hair cell here, outer cell here. So outer hair cell can lift it up or not. By doing so, it modulates this property. But what actually makes it do or not do is the brain. So people believe outer hair cell might play function in such things as talk to party. So when you pay attention to something, you are more sensitive. For example, if you have time, you can do this experiment. So if I say measure the threshold of audiogram on 1 kilohertz of hair threshold, you will know how to do this. So you can run your psychometric function given what we access at homework, measure this. But if I trick you, if you want to trick someone, you say, I'm going to measure you 1,000 hertz, play 100 tone, you told me here or not. But if you separately put a tone at 2,000 hertz, so what you are actually measuring is 2,000 hertz, but the person thought it was 1,000 hertz because he or she was told so. Pay all attention to 2,000 hertz. Then it turns out the threshold you measure out of the person at the 2,000 hertz is higher than if you told person, I'm going to measure 2,000 hertz. So when you pay attention to some particular sound, some quantity, your threshold is more sensitive. People believe that fact, among others, come from outer hair cell modulation, because that's how we modulate this. So another thing that's interesting is that I mentioned by passing that our ear is active device because of outer hair cell controlled by our brain. Our ear actually gives out the sound. This is called an autoacoustic emission. So if you send a tiny pulse into your ear and just listen, our ear can emit sound. This has become very useful clinically for certain diagnoses. So that's the first question: how is the sound generated into action? Then immediately after this, the second question is, I say until now I'll give you an example of 1,000 hertz, right? But everything I told you so far has nothing to do with 1,000 hertz. I could say 100 hertz, 10,000 hertz. Everything is still fine. But we do hear frequency in our hearing. How do we hear frequency? This comes from mechanical vibration. So if you take the talker, expand this, remember, talker is a hollow tube. If you expand it here, then that piece of membrane in the middle called basal membrane is like this. So when you vibrate talker, let's say by 1,000 hertz, somewhere on this dimension, there's a maximum vibration. But if you change the frequency to 100 hertz, 200, 400, 300 hertz, Then people discover in the 60s, the maximum vibration changes to the point that if you're near this end, okay, high frequency generates maximum vibration, and this end, low frequency generates vibration. That's based off frequency of here. Okay. So in that sense, using engineer's term, cochlear function as Fourier transform. Okay, you get a low frequency vibration, it generates most here. High frequency generates most here. Okay. So therefore, brain by listening to different parts knows what the frequency. So brain has no idea what is the frequency. All the frequency information is converted and memorized by the cochlear from here. Now, each of these places is connected to the brain. So in the sense that the cochlear is like a piano keyboard, okay? with low frequency key here and high frequency key here. That's how we hear. And the discovery of this is by scientists by Berkshire, and he won the Nobel Prize immensely for this work. So if that's not the case, then if you measure auditory nerves connected to different portions of the cochlear, they will have different receiving field sensitivity frequency. Okay? And so that's what it comes. So if we apply it like this, so let me summarize what I've told you so far. Cochlear, because of dimension, near the base is high frequency sensitivity. Near the top, we call it apex, it's low frequency. And because of the nerves connected to here, the auditory nerve connected to this portion has a high frequency, here a low frequency. Hair cell, very important, hair cell itself has no frequency information. Okay, we spent the last 10-15 minutes talking about hair cell. If I take a piece of hair cell, put a dishes, put a microscope and say what's frequency, you should not be able to tell. A low frequency and high frequency is the same as far as our conversation is concerned here. The frequency information comes because of where the hair cells is located. Now, this is connected by a bundle of the auditory nerve, 1 plus 6 of them. How many of them? In humans, there are 35,000 of them. So our cochlear is connected by a bundle of 35,000 individual fibers. Each fiber connects to one or few hair cells. So each fiber has its own frequency. So if you take example of these 6 fibers, if you measure the receiving field we talked about earlier, so that's their frequency. Pure by location. Very important. Frequency is generated by vibration in the cochlear. Okay. Now, so this organization we call phonotopic organization. This is the base of hearing frequency. Everything. So if you jump one step ahead, if the person lost all the hair cells, you as an engineer want to recover hearing, you know what to do now. You simulate this place to generate a high frequency hearing, you simulate here, generate low frequency hearing. That is the basis of modern cognitive because of this beautiful structure, one-dimensional medium. This is why we say earlier, all the voice we hear spectral overlapping, because there's a one frequency axis. All of us will begin to speak. Our frequency is about 500 hertz to 3,000 hertz. The wall be jumping on top of this. Okay. Now, some of you may ask, oh, you just talked about one frequency. What if I put 2 frequency, 3 frequency? What if when I speak, we have a 10 frequency? This is very much like a situation where you go to a piano keyboard, you push 1 key at a time or 10 key at a time. This is what we're touch upon here. That's the essential auditory system when we listen to speech and music, or listen to someone play piano with 10 fingers, or 8 or 9 fingers at the same time. The second thing is what we said earlier. I just leave a little bit hands here. Remember, I said if you have 1,000 hertz sinusoid, it vibrates through an ear, through eardrum, through a cochlear, through this fruit. Okay, it pushes the hair cell up and down, and pushes hair bundle forward and backward. Only this direction, channels open. Channel open, hyperbolic depolarization spike. This direction, no spike. Then you would expect, if you record from auditory nerve connected to hair cell, you should only see spike will go this way, not this way, right? Because this way is the channel is not open. That's exactly you need it, but it happened here. Okay. This is what happened here. If you give a sinusoidal stimulation, okay, you see they found, what is this? Okay, we just talked about last week. What is it called? What is this called? This part. Great. Post-stimulus histogram, or period histogram. We just talked about last week. That's why I brought up there. But there I did not explain why you have this. This is why you have this. You give the tone here. You see, this you won't have spike in half a cycle, not the other half. Why? It's because this hair cell only open this. So if you imagine, if the hair cell, whether this way, or depolarized, what would you have here? Would you have this form? This form will be flat. That term be the case if it's high frequency. So this property is very important. We're going to revisit that again. This is called fist locking. We already mentioned last time. Fist locking is a way for audio system to capture time structure. So this is very important for music and speech. So when we have a sinusoid going like this, there's time structure. If audio nerve only capture half of the cycle, naturally it will generate captures. So that means by reading here, the brain will know what its time is. But this only goes so far as about 3-4 kilohertz. Above that, we hear all the way to 20,000 hertz. If you play sound that's 500 hertz, then this does not vibrate fast enough. It becomes random. Therefore, you will lose phase locking, which is one of the word. We're going to come back to that paragraph. So these two properties of coupler, phonotypicalization and phase locking, are very crucial important concepts that you need to understand. So after we have representation of a sinusoid here and after, and the signal computer goes on to the next stage called cochlear nuclei. This is a processing stage with many neurons that we don't have much time to talk about. Just for time being, think about this processing. And then go to another stage called the superior audio. Now, here is the middle line of the word. You notice the signal here, beginning here, cross to our side. This is another subject of interest here, that we have 2 years. We have 2 years, we don't have 1 year. Why we have 2 years? Fossils to tell something from left to right. Okay. So until this point, all the neurons from a cochlear, audio nerve, and cochlear nuclei only receive input from 1 year. Then beginning from here, this goes to that. There's a mirror part that didn't apply. It goes here. So from here above, all the neurons receive inputs from 2 years. This is where we begin to process the sound from different location space. Okay. Then if you continue that, you go to thalamus. You continue that, go to primary audio cortex. This is the first stage of brain, somewhere right behind our ear. And if you continue that, then you go to cortical here. So now if we jump through all of the stage, come here. This is called primary audio cortex. The next stage is called secondary audio cortex. In primary audio cortex, if you pick up a neuron, if you drop your electrode here, test by frequency, the neuron would have a received field like a V-shape, sensitive to the frequency. How could this neuron in the brain have frequency mechanism? How? First, it's the fact that you record from one neuron here. This neuron might respond to 500 hertz. The neuron here might be 12,000 hertz. Where that information come from? Come from ear. So neurons, anywhere once you goes above cochlear, there's no new frequency information. The neuron in the brain has no knowledge what the frequency of sounds. The reason this neuron is sensitive to 500 hertz because it's connected all the way to the low frequency portion of the cochlear, which is at the top of the cochlear called apex. Okay. So it is all in this connection. It's all in this connection. So this connection all the way to the brain define how the brain hears frequency. Very important. The neuron in the brain do not generate frequency information by themselves. Now, after this, signal goes into an area called the work area that people believe are important for speech processes for some. And I will visit this some other time. So the third subject I'm going to finish in a couple minutes. First up is how time represented by neurofiber. Okay. So we said earlier, I give you 1,000 hertz. You actually can tell very well. So if you do a scientific experiment, I say measure how sensitive you can discriminate between two frequencies. You can do this now, right? We talk about this discrimination. Then you present two frequencies at a time, ask a person, same or difference. Take two frequencies randomly. You start at 1,000, 1,010, 1,000 or 1,100, easy. You say which one is that? You randomly mix them, same or difference. Some of the same, some are different. And initially, you can have a difference, delta F as 100 hertz. Everyone can do this. Then go to 10 hertz. Almost all of you can do this. Eventually, you will find out our discrimination of frequency in 1,000 hertz is about 1-2 hertz. Very, very funny, just very fine. So we can discriminate about 1-2, no more than 3 hertz out of 1,000. How can we do this? Because of phase selecting. Because the phase selecting capture time information. So that's how time is captured, right? So this is the slides you already saw of my last lecture that I took from here. You have a frequency here, 768 hertz, and the neurons can capture this by phase selecting. And we already talked about how would you quantify this, okay? And now, if you quantify that, take one of the major vector sweep or synchronous index, plot it here. But plot here as frequency sinusoid because that exercise you can apply to any frequency. This is the curve. Near here is best, is perfect. So what you can see here, our audio system can capture phase selecting time signals almost near as perfect, about 1,000 hertz, just altogether. Okay, totally. Then began to getting worse and worse. By the time you reach about 3-4 kilohertz, you're done. So here, we can hear 10,000 hertz, we'll do 20,000 hertz. About 4,000-5,000 hertz, there's no phase. So by predicting, if you were to do frequency discrimination between 5,000 hertz and something else, that delta is much larger than few hertz. Okay. Maybe one day you can try to do this. That's because of phase. Now, that's alternative. This is the next stage of calculus, nuclei. Okay, it's getting worse, and we'll explain that later. Maybe on Wednesday why it's getting worse. So the final question, and I want to discuss with you, which will take a bit more time, is how speech. So until this point, I think we have walked through a pure form, let's say 1,000 hertz, all the way from vibration to phase selecting to maybe 2,000 hertz or 500 hertz. That your choice. So next we're going to talk about if you throw in a voice, like speech, how does the brain process it? Just like you place several reality together. So we're going to do that. We need to discuss this Wednesday. Okay? Well, see you there.